just looked up at the night sky and really thought about what it takes to build a machine that can actually go there? We're not talking about just strapping a big engine to a tube. We're talking about engineering a vehicle to survive and function in, well, one of the most hostile environments we've ever encountered. This is a deep dive into some serious problem solving.
So that's really the big question, isn't it? How do you build something for the vacuum of space? You've got absolute zero temperatures right next to blistering heat. You're constantly getting blasted with radiation. It's a puzzle that pushes our technology to the absolute edge of what's possible.
And the answer? The key to solving this puzzle is what most of us just call rocket science. But if you want to get technical, the field is called aerospace engineering. It's this incredible mix of aerodynamics, material science, propulsion, you name it. It's the whole shebang that makes spaceflight a reality.
Okay, so where do we even start? Well, with the first and maybe the most violent challenge of all, just getting off the planet. To do that, you have to win an all-out brawl with Earth's gravity. And, the rule book for that fight, it was written a long, long time ago by Isaac Newton.
Think about it. A rocket sitting there on the launch pad is perfectly balanced. You've got gravity pulling it down and the launch pad pushing right back up. To go anywhere, you have to completely shatter that balance with an absolutely incredible, unbalanced force. And yeah, that's where the engines come in.
And this is where Newton's first law comes into play. It's pretty simple, really. That rocket is not moving an inch until some new, massive, unbalanced force shows up to the party. And that force has a name: thrust. So, how do you make that force big enough to matter? That's Newton's second law. It tells us that force equals mass times acceleration. In rocket terms, the more fuel you can burn, that's your mass, and the faster you can shoot the resulting gas out the back, the bigger your upward push. And that brings us to the big one, the most famous law in all of rocketry, Newton's third. For every single action, there is an equal and opposite reaction. I mean, this isn't just a phrase from a textbook. It's the fundamental law of physics that lets us leave the planet.
Here's how it works. The action is the engine throwing scorching hot gas downwards with unbelievable violence. The reaction is that gas pushing the rocket upwards with the exact same amount of force. And here's the key thing to remember. The rocket isn't pushing against the air. It's pushing against its own exhaust. That's why a rocket engine actually works even better in the total vacuum of space.
All right, so we've done it. We've escaped gravity's pull. We're in the void. But, getting to space is one thing. Actually navigating through it is a whole different ballgame. How in the world do you steer when there's no air for rudders and no ground to push off of?
Well, once you're up there, you've basically got two main options for moving around. You can think of it like a sports car versus a marathon runner. Chemical thrusters, that's your sports car. You get this huge, powerful burst of speed for quick maneuvers. But electric propulsion, like an ion drive, that's your marathon runner. It's this tiny, gentle push, but it's incredibly efficient and can keep going for months, even years. Perfect for those long trips across the solar system.
But it's not just about getting from point A to point B. You have to control which way you're facing. Engineers call this your attitude. And get this wrong, your mission is toast. If your solar panels aren't pointed at the sun, you run out of power. If your antenna isn't pointed at Earth, you can't talk to anyone. So yeah, attitude control is absolutely non-negotiable. So how do they do it? Well, first, you have sensors, like star trackers, that look at the constellations to figure out exactly which way the spacecraft is pointing. Then, you've got actuators that actually make the turn. These can be tiny little thrusters that puff out gas. Or, and this is the really cool part, they use things called reaction wheels. Just imagine you're floating in space and you spin a bicycle wheel clockwise. Your whole body would start to turn counterclockwise, right? That is exactly how a reaction wheel can turn a giant satellite, just by spinning a weight inside of it. So clever.
So, we've launched and we can steer. Awesome. But now we face the biggest challenge of them all, just surviving. Because space is a place that is actively, constantly trying to destroy any machine we send out there.
I mean, the list of threats is just relentless. You have ionizing radiation that can fry sensitive electronics, plasma that causes electrical shorts, temperatures that swing hundreds of degrees, from hotter than an oven to colder than liquid nitrogen. And on top of all that, you're flying through a cosmic shooting gallery of micrometeoroids and space junk,
with every piece moving faster than a rifle bullet. So the engineering solution to this constant assault is something called the spacecraft bus. The best way to think about it is like the chassis and engine of a city bus. It's the main body that holds everything together and provides all the life support needed to protect the really valuable part, the payload, which is just the science instruments or cameras that are actually doing the mission. The first piece of that bus is the structure itself, the skeleton. It's usually made from really advanced stuff like carbon composites or special aluminum alloys. It has to be unbelievably strong to survive the bone-shattering vibrations of launch, but at the same time, it has to be incredibly light because every single gram costs a fortune to hurl into orbit. Next up, you have the heart of the whole operation, the electrical power subsystem. If you're near the sun, this usually means big solar panels. But for missions way out in the dark, like to Jupiter or beyond, they use what are basically tiny nuclear batteries that turn the heat from decaying plutonium into electricity. Whatever the source, if this system fails, the mission is over. No power, no mission. It's that simple. And to deal with those insane temperature swings, you need a thermal control subsystem. It's pretty much the spacecraft's HVAC system. It uses layers of shiny insulation, looks like foil, to keep heat in, and big panels called radiators to dump any excess heat from the electronics out into the cold of space. The goal is to keep everything at a nice, stable, happy temperature. And believe me, failures in these systems have very real consequences. This isn't just theory. Some of the most famous spacecraft ever built, from Voyager 1 to the GPS satellites that you and I use every single day, have had mission-threatening problems. Sudden power resets, getting false commands, complete shutdowns, all because of the brutal environment of space. Getting these survival systems right is absolutely everything.
So when you put it all together, from the physics of launch to the struggle for survival in orbit, you start to realize that a spacecraft isn't just one single invention. It's really more like a symphony of deeply interconnected systems. Every single component, from the engines and the power systems to the structure and the thermal blankets, has to work together in perfect harmony. A failure in one tiny, seemingly insignificant part can cascade and doom a billion-dollar mission. This incredible, high-stakes ballet of technology is the real genius behind engineering a spaceship.
I mean, just look at this. This is a real-world propulsion module. You can see the fuel tanks, the structural trusses holding them in place, all the plumbing, the wiring, everything we've been talking about, all intricately woven together into one functional piece of hardware. It's amazing. It's like Dr. Mike Runtman said, designing a space mission is an interdisciplinary sport. You have mechanical engineers, software gurus, physicists, and materials scientists all having to be on the same team because every single decision one of them makes affects absolutely everyone else. It really is a staggering achievement of human ingenuity when you stop and think about it. We've built a machine that can defy gravity, navigate the endless void, and survive in one of the deadliest environments known to us. And that leaves us with one last, really exciting question. Now that we know how to build them, where should we go next?